Good morning. We are doing the Chapter 12 review today. We'll start by going over Chapter 12 homework number 7 on percent yield. What is a percent yield? If 4.65 grams of copper is produced, so this is the experimental value, is 4.65 grams of copper is produced when 1.87 grams of aluminum react with excess copper sulfate. Okay, so we have a balanced equation here, and we have a mass of aluminum that we're beginning with, and so therefore, theoretically, there's a certain amount of copper that we should produce. So to figure out what that is, we do just a traditional conversion table that we're already used to. Getting into grams of copper is where we want to go, and we're going to start with the 1.87 grams of aluminum as our starting point. So, like always, get out of grams of aluminum, get into moles of aluminum. Periodic table tells you 27.0 grams per mole. Then use the balanced equation to switch from moles of aluminum into moles of copper. Balanced equation says 2 aluminums will produce 3 coppers. And lastly, our last step is to get out of moles of copper and get into grams of copper. And periodic table tells us 63.5 grams of copper per mole. Now we use our calculator to find out what that is. Once we use our calculator to find out what that is, we get 6.60. So this is the theoretical yield. Theoretically, we're supposed to produce 6.6 grams of it, but because of whatever happened with our experiment, we only produce 4.65 grams. So you divide the experimental yield by the theoretical yield, and we see that experimentally we only yielded 70% of what we should. Okay. Question number 31, heating an ore of antimony, antimony sulfide with a molar mass of 679.4 grams per mole in the presence of iron gives the element antimony and iron sulfide. When 15 grams of antimony sulfide reacts with excess iron, we produce 4.84 grams of antimony. So this is the experimental values. What is the percent yield? All right, so theoretically, 15 grams of antimony sulfide probably is supposed to produce more antimony than 4.84. The only way to tell for sure is to work that conversion table and end up with grams of antimony. So step number 2 is we're going to get out of grams of Sb2S3 and get into moles of Sb2S3. Periodic table. Oh, no, not periodic table. Given in the problem, 679.4 grams per mole. And then step number 3, get out of moles of antimony sulfide, get into moles of antimony. Balanced equation looks like it's a 1-to-2 ratio. And one more step, get out of moles of antimony and get into grams of antimony. Periodic table is going to tell me that number. I can't quite see it up there, but my next slide will have that number too. And that will tell me how many grams theoretically I'm supposed to produce, which is 5.38. We only produced experimentally 4.84. So the percent, I don't want to say percent difference. Let's keep with percent yield. The percent yield is that experimental number divided by the theoretical number. Okay, and we get that this one came out to be 90% efficient. You can see this would be an important thing in chemistry because if a chemical reaction is designed to produce something that has value, then we want to maximize how much antimony we get out of the ore, antimony sulfide. Question number 32, 4.68 grams of sulfur tetrafluoride. Let's put a 4.68 here. I'm not sure why I don't have this already balanced. Reacts with excess I2O5. The products are IF5 and SO2. I couldn't tell you one thing about this reaction, but I do know that it says in an experiment that the sulfur dioxide, the experimental value is 2.50. We want to know what the theoretical value is so that we can find the percent yield. We do need a balanced equation. A 4 and a 5, that's an oddball. So I'm going to put a 5 in front of SF4, and this could be ugly, and a 4 in front of the IF5. May or may not work. Got to try something, right? Then this tells me that I need a total of 4 iodine, so I'll put a 2 here. That gives me 10 oxygens and 5 sulfurs. Hey, look at that. A 5 there gives me 5 sulfurs and 10 oxygens. Worked out, even though for a little while I was a little nervous. All right, these are the experimental numbers. We want to know theoretically, what should that 4.68 grams of sulfur tetrafluoride should have it produced? So 4.68 grams of SF4, and we want to get all the way over to grams of SO2. Get out of grams of SF4, get into moles of SF4. We'll see that number on the next page, going to our periodic table to add up all of that. Then get out of moles of SF4 and get into moles of SO2. Is a 5 to 5 ratio. And then last step is get out of moles of SO2 and get into grams of SO2, around 64. And then do the math. Once you get this, you have your theoretical value. It's bigger than 2.5. 2.5 divided by 2.77 gives us 90% efficiency. Okay? Those are your homework. Nope, we have one more. Silicon dioxide, we have 50 grams of it. Reacts with excess carbon to produce 32.2 grams of silicon carbide. Balanced equation, well, regardless of what the balanced equation is, I know this is going to throw us off a little bit, but when I go to do my math, there's one silicon found in each of these. They're in a 1-to-1 ratio. Even if that ends up balancing differently, it could be 2 to 2 based on us having to move stuff around. But the silicons are in a 1-to-1 ratio, which tells me that these two substances are in a 1-to-1 ratio. That's a nice skill going forward into AP chemistry. I think it actually works this way anyway, because we have 2 oxygens. If I put a 2 here, that gives me 2 oxygens, 2 carbons, plus 1 carbon. I think I need a 3 right there to make that balance. Okay. Then, since these are our experimental values, let's take the silicon dioxide and let's find out theoretically how much silicon carbide should it have produced. So we're going to do the same thing. Get out of grams of SiO2, get into moles of SiO2. Periodic table will tell us that number, so we'll the next slide. Then get out of silicon dioxide and get into silicon carbide. And like I said earlier, I knew it was going to be a 1-to-1 ratio because these are the only places that silicon is found. So they have to have the same number in front of them, a 1-to-1, a 2-to-2, so on and so forth. And then lastly, let's get out of moles of silicon carbide and get into grams of silicon carbide. Periodic table will tell me both of those numbers, and then I can use my calculator to get that answer. And then 32.2, I'll bet you, is smaller than that answer because theoretically, we always produce more than we do experimentally. Until we get 30, yeah, because that still works, 33.4. Then 32.2 divided by 33.4 gives us 96%. Sorry, I brain faded there for a second, thinking that should be the smaller number. I was going to make a joke prior to that about labs that do that. Because it does happen sometimes in labs, especially when they're water-based. Because what happens is if you don't get all the water out of there, you think you have a larger mass experimentally than you actually do, because it's plus water. So sometimes it makes our percent yield look like it's greater than 100%, just tells us that we have air in a different direction. Now we have the review. There are 6 questions on this review. My suggestion to you is pause the video and do each of the questions individually, and then play, see what I do, and then move on to the next one and pause again and keep going through this. Don't just watch me do it. That doesn't help you on your test. You need to try it first. So try number 1 first. Okay, we're back together again. Carbon disulfide is an important industrial solvent. It's prepared by the reaction of coke with sulfur dioxide. No, that's not cocaine. No, that's not Coca-Cola. It's just coke is just maybe like a, I don't know, is it the powdered form of carbon when they're using it industrially? Could be just a piece of charcoal, but we want it pure. All right, how many moles of carbon disulfide form when 2.7 moles of carbon react? We'll assume that there's an excess of sulfur dioxide. I need a balanced equation first of all. There are more than 1 carbon on this side, so I don't really want to start with carbon. I want to end with it. I'm going to start with sulfur. Since there's 2 here, I'm going to put a 2 in front of the sulfur dioxide. That gives me 4 oxygen, so I'll put a 4 in front of the carbon monoxide. That gives me 4 carbons plus this 1 carbon means I think I want a 5 in front of the carbon on this side. See how I had to save the carbon for last because it required the adding up of things that still had to be figured out first. If you would have started with a 2 there, you'd have been going in circles. All right, so we have 2.7 moles of this, and we want to know how many moles of this. This is just a 2-step conversion table. Going to require us to get out of moles of carbon and get into moles of carbon disulfide. 5-to-1 ratio. So we're dividing 2.7 by 5, and my calculator said 0.54. Question number 2. How about let's pause and give you a chance to work on it. All right, you're back with me again. Methanol is used in the production of many chemicals. It's made by reacting carbon monoxide with hydrogen. We've got, looks like we already have a balanced equation, and we want to produce 360 grams of methanol. How many moles of carbon monoxide are required? Our balanced equation is only going to take 3 steps. First step, write down your given and put your question. Second step, get out of grams of your given and get into moles. Periodic table says 12 plus 16 is 28 plus 4 more is 32. 360 and 32 so far. Next step is use the balanced equation. Looks like it's a 1-to-1 ratio. We're getting out of methanol and we're getting into moles of carbon. Sorry, I'm in trouble writing here. Pen's not following everything I am. Now you'll notice I made my conversion table long enough for a 4th step where we would get out of moles and get into grams. That's a common thing to do. That's what we kind of do as a robot. But that's not what this problem asks. This problem just says how many moles. So I'm going to stop right there. I'm going to get rid of that last line because this already, when you're looking your units through the problem, we see we cancel out. We're left with moles of carbon. So do the math with the calculator. And I got 11.25 is what the calculator screen shows. But because 360 only has 2 significant digits, I'm going to round that to 11 moles of carbon monoxide. Numbers 3 and 4. Sure, pause for a moment. Try number 3. All right, you're back with me again. So, feels like a conversion table problem, right? Feels like math. How many grams of fluorine? So, this is where we're going, and this is where we're starting. 66.6 grams of fluorine and 66.6 grams of ammonia. Step number 1, write down your givens. Step number 2, get out of grams of your starting value of your starting substance and get into moles of the substance. Periodic table says 17.0 grams per mole for ammonia. Now that we have successfully gotten out of those units, we're now in moles of ammonia. Let's get out of moles of ammonia. Oops, sorry, I'm writing it backward. NH3 and get into moles of our answer, which is fluorine. Balanced equation says 2 to 5. And then last step, get out of moles of fluorine, get into grams of fluorine. 2 fluorines from the periodic table adds up to 38. And then cancel out the units, and we're left with grams of fluorine. And the calculator says 372, 3 significant digits. Question number 4. Give you a moment to think about that one. Try it. All right, we're back together again. So we have 1.49 grams of nitric acid. Sorry, brain faded for a second. How many atoms of zinc? Ooh, we haven't seen that in a while. So our conversion table this time, Avogadro's number is going to rear its ugly head as we go through this. We want to end up with atoms of zinc, and we have 1.49 grams of HNO3 to begin with. So there's step number one. Step number two, get out of those units and head towards the mole. I don't know, let's look at the next slide. Periodic table says 63.0. Now that we've done that, we've effectively gotten out of the units of grams of HNO3. We're into moles of HNO3, which means we can now head to our balanced equation and switch substances between moles of HNO3 and moles of zinc. That was a 10-to-4 ratio. That's an odd one, but it is what it is. We got out of moles of HNO3. Now that we're in moles of zinc, we're going to get out of moles of zinc and we're going to head towards the answer unit, which is atoms of zinc. 1 mole, Avogadro's number, 6.02 times 10 to the 23rd atoms. Moles cancel out moles. We now have the right answer units, and now it's our calculator's job to help us out. My calculator said 5.7 times 10 to the 21st atoms of zinc. 2 more. Question 5. Ammonium nitrate decomposes explosively at high temperatures to form nitrogen, oxygen, and water vapor. What is the total number of liters of oxygen gas formed when 228 grams of ammonium nitrate decompose? Give you a moment to solve that one. All right, we're back together again. So you're going to start with step number 1, writing down your given. And while you're at it, why don't you also write down your question, liters of oxygen. Then step number 2, get out of grams of ammonium nitrate and get into moles of ammonium nitrate. We're going to need to go to our periodic table. Mine said 80. Grams cancel out grams. We're now into moles. Now we use the balanced equation to get out of moles of ammonium nitrate. I know it's a pain to write these things down, but you only have to do it a couple times on your test, so take the time and do it. Looks to me like our balanced equation is just 1-to-1 between those two. Get out of moles, we're into moles. Now that we're into moles, let's get out of moles and get into liters. At STP, 22.4. Odds are this did not occur at STP because if it decomposes explosively and requires high temperatures, then it's going to be at a high temperature. But once we have the gases, we can collect them, cool them back down, and pressurize them down to standard temperature and pressure. And that way we are allowed to use 22.4. We'll do that next chapter with the gas laws. Plug all that into your calculator, and mine says 63.8. Last problem. Looks like we have 2 given numbers here, huh? The minute you see 2 given numbers, you're thinking about 2 types of problems, either the limiting reactants like this one, or percent yield like we just went over. You know this isn't percent yield because it doesn't talk about what is the percent yield. You know this is limiting reactants because they give you 100 grams of carbon and 85 grams of B2O3. Okay, so it has to be a limiting reactant problem. So we need a balanced equation, which of course will be given on the test. So let's just balance this together right now. I'll put a 2 in front of the B2O3. Gives me 4 borons on both sides. Gives me 6 oxygen. So I'll put a 3 in front of the CO2. Sorry, my brain's just working ahead. It's going, oh, this doesn't look good. It looks okay because carbon's going to help us out here because we have 3 plus 3 more is 6. Since we have singleton carbons there, we can just put whatever number we want to in front of that. And a 6 would make that balance perfectly. So 2, 6, 1, 3. Okay, we're using up the carbon at a really, really fast rate, but we have a lot of it. So which one's the limiting reactant? I can't tell. I have no choice but to work this one out as 2 separate 2-step conversion tables where I get out of 85 grams of B2O3 and get into moles of it. Do you want to call that diboron trioxide? Go ahead. Could it be called just boron oxide? I don't know. I don't know if it's just the only form of that substance, but diboron trioxide would certainly work. And then I need to go to my periodic table for that. Meanwhile, 100 grams of carbon get out of grams, get into moles. That's a 12. I don't know what I have on my next slide. I have it all worked out. So let's just go back, 8.33 and 1.22. Let's also go back one more time. Oops, that was the wrong direction. Oh, I have them backward. 69.6. I'm upside down. So 69.6, and these numbers are backward. Can I remember those numbers? Okay, without going forward, look that over to decide who's the limiting reactant. All right, that was enough time to think about it. If they are reacting in a 2:6 ratio, that means they're really acting in a 1:3 ratio. So 1.22 times 3 is only going to be like 3.66. We've got 8.33 moles of carbon, which means that we've got plenty of it. Even though it's reacting at a much higher rate, we've got so much of it that this is our limiting reactant. So now I'm going to finish the conversion table using that. Or you are. Get out of moles. Where are we heading to? How many grams of B4C3? Get into moles. 2 to 1. And then one more step, get out of moles of B4C3 and get into grams. Now I'm going to go to my last slide because I can just let it tell me what that molar mass is. How about 79.3, which gives us 194 grams. All right, so that's your review for the Chapter 12 test. The only thing that did not show up on the review was a percent yield. But we did 4 of those in the homework questions from last night, so make sure you look at those 2 while you're studying for your test, and I will see you when I see you.